Okay, so when today is going to be the last class for about a month. Our next class will be, I think, on the 30th of April, when we'll sort of continue. Okay, in today's class, we're going to end our discussion of formal properties of string amplitudes today. So when we come back, we will begin by discussing the requirement of conformal invariance of the alpha prime expansion to try to derive beta function. Sorry. Hello? Yeah. Separate, please. Why was one separate? One separate. Okay, thanks. Okay, yeah. So we'll go as anything we can say today we do, and we should spend into the time of this. Perhaps have to go a little faster than the usual class, just try to cover it. Okay, so first clearing up loose ends from last time. Last class we were discussing three amplitudes of the sphere, and we completely understood all the singularities, all imaginary parts of these amplitudes in terms of we found that these singularities were exactly all associated with propagation of intermediate particles in finite vectors. Okay, and thereby we concluded that string amplitudes obeyed the unitarity properties of obeyed the unitarity conditions that gave that the space-time restrictions of unitarity. In the same way, the final diagram expansion does. Okay. There were two loose ends. The first loose end was this business about the B0 delta. But that's exactly as we discussed, as Lobnagon suggested last. That goes exactly as Lobnagon suggested last class. Essentially, the 2-point function between B and C is non-zero. Between C and C is 0 and C and B is 0. Okay, so if you want the same states, namely states that are annihilated by B on both sides, then you need to have explicit factors of B0 and B0 tilde, which is what we had last class. Okay, so the factors that we had last class is what was needed in order to make both states physical, because the inverse metric that connected the two states would otherwise have connected a state that is annihilated by B with a state that is annihilated by C. Okay? So to convert that state that's annihilated by C into a state that is annihilated by B, namely a physical state of string theory, you need those extra factors of B0 and B0 tilde. So those factors were there, and they were precisely demonstrated. Okay? The second thing that we didn't have time to talk about last class, so let's quickly turn to that, was that we seem to be getting unitarity, except that what was running in the channels was all states of string theory. All states that came out of the conformal field theory. Because remember, what we used was a completeness sum conformal field theory, and not merely the states that obeyed that laid Q cohomology. You remember we inserted a complete set of states, those are complete set of states of the conformal field theory, and that was all states. However, as you know, we have a physical state associated only with a state of the conformal field theory that lies in Q cohomology. So in order for this really to be consistent with space-time unitarity, we must have that the contribution of all states that are not in Q cohomology vanishes. Okay? And how does that work? Well, this works in a very simple fashion. Okay, so let's see this in detail. Okay, you see, first I'm going to remind you of the representation theory of an operator that squares to 0. So an operator that squares to 0 has two kinds of irreducible representations. Okay, the first kind of irreducible representation is two-dimensional, and the second kind is one-dimensional. The two-dimensional representation is made up by a set of states A and B, such that B is equal to Q and A. Okay, and therefore Q and B is equal to 0. Okay, so if you wrote this out in a matrix, you get 0, 1, 0, 0. Okay, the second kind of irreducible representation is when Q acts on some side and you get 0. That can happen. You just state that's annihilated by psi, and with the condition equals 0, and that there is no state, there is no psi prime, does not exist a psi prime such that q of psi prime is equal to psi. Not true. Okay? So these are the states that we call physical states. They are annihilated by Q and are not Q exact. These are the states, these states that are like B are the states states that are like A are states that we call unphysical. Because they are not annihilated by Q. And states that are like B are annihilated by Q, therefore they are physical, but they are Q exact. Okay? So they are pure gauge states. Okay. Now the key point is that there is a one-to-one map between unphysical states and pure gauge states. Because if a state is pure gauge, it is Q of something. Therefore, that something that is Q of is not annihilated by Q. Okay? So irreducible representation of this Q operator, always move to a basis such that this Q looks like 0, 1, 0, 0, many blocks of these, and then blocks in which just zeros exist. Okay? So the physical states, the unphysical states, and the Q exact states are paired with each other, whereas physical states stand alone. Is this clear? Now, what I'm going to do is to take all of my conformal field theory and take any basis of the unphysical states. Okay. Let's call some I unphysical. Okay, this is in general infinite dimensional basis. You can grade it with energy, in which case it will become finite dimensional and everything we say will become well defined. Okay, great. Then this defines a natural basis on the space of Q exact states. Okay, so Q on I unphysical gives us a basis for the state of the space of Q exact states. Okay, and then I will also add J physical in an arbitrary set, an arbitrary basis in the remainder of Hilbert space, a basis that's needed to complete this into a basis of all of Hilbert space. Okay, this gives us a basis in this space of physical states. This thing, by the way, is of course not terribly well defined. It's very choice dependent, because to a physical state you can always add a Q exact state and then remain physical. Okay, but I'm not saying that it's a unique basis. I'm saying choose any. It's not even a unique space.
Yeah, but a complete, for it to be complete state, complete Hilbert space, like you do not need to take into account physical plus the Q exact states.
We've already got a basis. You choose any basis of physical. We've chosen a basis of non-physical states. We've chosen a basis. We could, do it more. Anyway, but we've chosen a basis of non-physical state. We've chosen a basis of Q exact states, and after that, we choose an arbitrary basis of physical states. What is a physical state? Well, you complete the basis of Hilbert space. Any completion will give you a state that cannot be written as a linear combination of unphysical states, therefore not unphysical, and cannot be written as a linear combination of Q and some, therefore not exact. Okay? Now, there's great deal of arbitrariness in all these choices I've talked about, especially the last one. Because suppose you give me a basis of physical, of physical states, I can add to that some linear combination of the Q on something in states and it will remain physical. Right? Because it's really, the thing that is really defined is cohomology classes. Okay? So that changes not just our basis but also our space. But we won't care. It won't matter for this. Okay? So I just define some basis. It's always possible to define some basis like this. That's all that I'll do. Okay. Then, in the basis that once I've chosen this basis, I define a projection operator P that projects onto physical states. Okay? So this is the projector onto the space spanned by the spaces. Okay? So P on JP equals JP, and P on all of these is equal to P on I on physical is equal to P on Q times I on physical. Okay? And the next thing I do is to define an operator U, which does the following. It inverts the action of Q, but only on Q exact states. That is, U on, I define this operator such that U on Q times I on physical is equal to I on physical. U on I on physical is equal to 0. U on J physical is equal to 0. Okay? This gives me an action of each of these operators in my basis. It's totally well defined. Since these are linear operators, so I define the action on the basis, I define them anyway. Okay. Now, in terms of these operators, let me make the important claim. The identity operator can be written as P plus Q plus U. Let's check. Suppose we act on a physical state. Okay? We get back to physical state because P on the physical state gives us back in itself. Q annihilates physical states, and by definition, U annihilates physical states. Okay? Suppose we act on an unphysical state. P annihilates it. Now, U annihilates it. Q doesn't annihilate it, and U inverts the operation of Q. So I get back the unphysical state. On the other hand, suppose I act on an exact state. It's annihilated by Q, it's annihilated by P, but U removes the Q and then I add Q again. So once again I got the same exact state. Okay? So with my definition of P and U, okay, you see what we do, what these definitions are, right? In these 2 cross 2 blocks, U undoes the operation of Q, but it can't undo the operation of Q on physical states, so it doesn't do anything. It's the nearest to an inverse that exists for the Q operator. It's the nearest to an inverse operator. Okay? With this, we demonstrated that identity is this. Okay? So, now, let us remember what we did. We used the fact that a complete that
U is a fermionic operator.
U is a fermionic operator. That's right. And because Q is. Okay. So remember what we did in order to get this unitarity. We inserted identity, which we then expanded as a complete set of states. Okay, so let's insert identity. Okay, but since in this identity insertion, Q acting either on the left or on the right annihilates everything. Remember what we had? We had A, B times. Suppose you had some Q here. This gives you 0, as we bounded in many ways. Right? We bounded either from operator reasoning or from contour integral reasoning, right? Because Q is the integral of the BRST current, and that can just be pulled around the sphere to give you 0. Right? Because each operator in the circle will also give you 0 because those are all BRST there. Okay, so as Q acting either on the left or on the right gives you 0, we can just forget about these. So inserting identity for the correlation functions we're computing is the same thing as inserting the projector onto physical states. So we can restrict our sum of states that appears in the decomposition of identity to the sum of states over physical states. Okay? So although in our formal arguments we did a complete sum, we resolved identity into all states, the contribution from unphysical and Q-exact states vanishes. Okay? So that's the key point. And it's a little obvious if you think about it. The point, just said a little more colloquially, is that it's very much like this BC business that we talked about. That in the completeness sum, okay, an unphysical state is accompanied by a Q-exact state, or a Q-exact state is accompanied by an unphysical state, and one of the two annihilates the other on the left of the plate. It's very much like how it happens in QED. Yes, in fact, there's a precise. If you restrict to the master set, that this would be what happens in QED logic. You see, it's just you reduce to the lower end, you get the same argument in field theory. Okay, fine. Okay, so that completes our discussion of unitarity of tree-level string theory. As you see, we've done it in a very, very explicit. Well, it's formal because of all this completeness stuff. But in a way, the key point is that we relate two beautiful structures, namely the structure of the OPE on the world sheet and the structure of the Hilbert space interpretation of the world sheet. You see, actually, it's the second thing that's more important. See, until 2 or 3 lectures ago, we pretended that field theory was just defined by path integrals, more or less, right? That's all we need in order to compute string theory. But in order to isolate the singularity structure of string theory diagrams, it was very useful to remember that there's another important element in quantum mechanics. There's one way of thinking of this through the path integral, but the second way of thinking through Hilbert spaces. And that was the useful way of thinking in order to understand the singularities of quantum diagrams, the imaginary parts of quantum diagrams. And in particular, the completeness sum is a very useful device. Okay? So it's this interplay, the fact that you can take this path integral and cut it, always have this Hilbert space interpretation. And in this Hilbert space interpretation, you can then isolate the singularities of quantum diagrams that allows us to understand the precise nature of these singularities and to demonstrate that they're going to be trade for trade advantages. Is this clear? Questions or comments about it? Okay. Now, I'm going to tell you how the same analysis or very similar analysis generalizes to loop level diagrams. Okay? Now our discussion is going to be more schematic than the tree level thing. Basically because in order to give you a really satisfactory discussion, but in order to demonstrate each claim that I'm going to make, we will have to veer off into a lot of mathematics about the structure of Riemann surfaces that we'll not go to that. Okay, so I'm going to be asserting some statements about Riemann surfaces, as you will see. Pulczynski gives references to places where these statements are proved, if you're interested. Okay. So before we start, what is our goal? Our goal is to understand two things. Our goal is to understand the statement that you've heard of, that string perturbation theory gives you finite results, or at least has no UV divergences. We saw an example of this for the active magnitude for the torus. We want to see this in modular. We want to see this in modular gravity. The second thing we want to understand is that string theory gives us the rules of string perturbation theory give us results that are guaranteed to be consistent with unitarity. These two things we want to understand. We're going to do this in a formal way, but just to see, where it comes from. Okay. So, in order to try to address these questions, the first thing we have, you see, where do divergences in field theory come from? Divergences in field theory come from integrating over Feynman diagrams. doing this integral over Schwinger parameters, the moduli space of final diagrams, if you like. Okay, so of course, if you have divergences in string theory, its origin will be the same place, doing the integral over the moduli space of Riemann surfaces. Okay, so the first thing we have to do in order to address questions about finiteness and, as we'll say, also about unitarity, is to understand the moduli space of Riemann surfaces a little bit. Okay, so that's our goal, and for this purpose, I'm going to introduce a construction that allows you to construct higher genus Riemann surfaces, starting with lower genus Riemann surfaces. And this construction has some findings on plumbing fixtures. Yeah, the plumbing fixture. Okay, you'll see why. Okay, so good. So the first thing I'm going to do is introduce you to the plumbing fixture. Okay, so suppose you got two different Riemann surfaces. If you want, you can imagine them to be spheres, but they could be anything. Okay? And I've got a coordinate patch. Remember what a Riemann surface is. A Riemann surface is a manifold, defined in a theory where Weyl transformations are reached. Okay? So different patches on you can write it patchwise as complex space with an arbitrary conformal, which is with a metric that is dz bar, which is conformally related to dz bar, and there has to be a coordinate change where it overlaps, under which the metric matches up to a Weyl factor. The Weyl factors are regular sum. Okay, so consider one of these coordinate patches in which the metric is some Weyl factor times dz bar. Okay, and consider another patch here, which has the same, so this coordinate patch defined here, and let's call this Z1 coordinate patch, and let's call this the Z2 coordinate patch. Okay, and let's say that this coordinate patch is defined up to mod Z1 is less than mod Q to 1/2 for some Q. And similarly, the other coordinate patch is defined up to mod Z2 is less than mod Q to 1/2 for the same Q. Okay, now what I want to do is to define a new Riemann surface in the following way. I'm going to remove a disk from here, remove a disk from here, and then join these two things. Okay? So the idea is to remove a disk and join these two things with the tube. Okay? But we have to do this in a way that specifies complex structure. Okay? So that's why what we're going to do is remove not the whole disk all the way up to Q, but only up to, so we will remove a disk which is mod Z1 is less than square root Q, square root of mod Q, times 1 minus epsilon for some positive epsilon. Okay, so we're not removing all of the disk, only some part of it. Similarly here we will remove mod Z2 is less than square root Q, square root mod Q, 1 minus epsilon. We're not removing all of the disk, only some part of it. And then what we will do is to identify points in this annulus and this annulus. Okay? We will identify points. We will identify points. No, just identify points. So we remove these disks, and in the remaining regions we identify points according to formula. So that identification now joins these two things. This is the tube. This remaining part is the tube. The tube that joins things. Okay. So we identify points according to the formula. Let's see. According to the formula. And so I'm going to require this thing be defined. Sorry. I'm going to require this coordinate patch be defined not only up to square root q, but square root q over 1 minus epsilon. Just because we identify it. Of course, it doesn't matter. I can choose q to be so small that it will be q. As long as there's a neighborhood. There's epsilon. Sorry, so this is my requirement. Okay, I choose some epsilon which is 0.1. Okay, and I choose some q such that these coordinate patches are defined in this region, in the slightly larger region. Okay, and then the identification we do is the identification z1, z2 is equal to q.
In that angular.
What?
In that angular.
In that angular region. So what does it do? You see. So what the angular region that remains, let me use another color, was between square root q into 1 minus epsilon and square root q into 1 plus epsilon. Okay, and maybe I want I think I want to square. Sorry. Let me put it. It's okay. We have the same thing here. Okay, sorry. Sorry. Let's take that. It wasn't. Okay. So this is the angular region that remains after not removed. Okay. Now, according to this identification, this inner end here will match over to the outer end here.
So the rest of the thing will be like replaced by the. I mean, as if we have replaced the inner disk by the rest of the.
As if we replace the inner disk by the remaining Riemann surface. Okay, so this inner thing here maps over to the outer edge here. The outer edge here maps over to the inner edge here. And these two things are conformally related because z goes to 1 by z is a conformal transformation. Okay, so what have we done? Suppose this Riemann surface was defined by a whole lot of coordinate patches, including the one we concentrated. Okay, this Riemann surface was also defined by its coordinate patches, including the one that we concentrated. Right? Now we've got a new Riemann surface with as many coordinate patches as there were in the sum of these two surfaces. Because we have this coordinate patch, now we've got an overlapping coordinate patch in this surface that meets over to the rest of the surface, and all the remaining coordinate patches that already existed in both different surfaces. Okay, and we've given the rule for how points the diffeomorphism, how you should relate points in this coordinate patching and this coordinate patching where they overlap. That's the rule. Okay, so this is a clean specification of a complex manifold. Is this clear? Okay, of course, all that changing epsilon does is change how thick the overlap region is. So as long as epsilon is non-zero, it doesn't change anything. Okay, so the manifold itself is specified just by Q. Which our choice of coordinates z1 and z2, and by the parameter q, epsilon is just some intermediate construction, and that will enter into the specification of the manifold. Okay, but once you've chosen your coordinate charts z1 and z2, q is a property. I mean, affects the complex structure of your manifold. If you change, you have a choice of the two things. You could either change q, or you could redefine your coordinate chart z1 by some factor of q, Okay, and that will give you a new complex manifold. Okay, is this so given two complex manifolds with two distinguished coordinate charts centered around 2 points, okay, there is a way of connecting them up to give you a complex manifold. Is this clear? This thing is called the plumbing fixture. Is this clear? Okay, great. Now, so for instance, let's look at an example. Let's look, for instance, at an example. Suppose you had, and by the way, this fixture can be done either on two separate manifolds or on two different coordinate patches of the same manifold. Okay? So suppose we have a sphere, and we have coordinate patch here and coordinate patch here. We do the plumbing fixture, that will give us the torus. You see, if we have a torus, now we have patch here, we do the fixture, it will give us genus 2 surface. And so on. So this plumbing fixture can be used to construct higher genus Riemann surfaces starting from lower genus Riemann surfaces. Okay. Now we address the following question. We address the question, can we build an arbitrary Riemann surface? Okay? Can we build an arbitrary Riemann surface? Okay, let's try to do the following thing. You see, suppose we had a sphere with 3 pouches, with 3 coordinate patches. Yeah, another sphere with 3 coordinate patches. You see, we can build the torus by doing this with this and this with this, for instance. We can build a higher genus surface by doing various other things. Then if you have more spheres with 3 coordinate patches, you can do more. Okay. You can convince yourself, basically, that given an arbitrary number of spheres with 3 coordinate patches marked on these 3 spheres, you can build a genus Riemann surface of arbitrary genus. Okay? And the way one may think of this is in sort of final diagram. You see, associate with each of these spheres a trilinear vertex. Okay? And every time you you sew together surfaces on particular patches, just join up the propagators. Okay. So suppose you did this, and what you have is this one loop thing with 2 vertices that were still left over. You can use them for external particles, right? Okay. Suppose you want to build something that is 2 loop. Okay, what would you do? So let's see. So suppose you have something like this, you have something like this, and then you have something like this. All you have to do is to make a 2-loop Feynman. Okay, that would be a genus 2 surface with one point mark. If you want more points marked, you split this up in 2. Okay, so basically this plumbing fixture here, starting with spheres with 3 marked points, so 3 coordinate patches, and using the plumbing fixture, you can build up Riemann surfaces of arbitrary genus. Okay. Now, a question that you might ask is the following: is there a systematic way to cover the entire moduli space of genus G Riemann surfaces? Okay, to cover the moduli space of genus G Riemann surfaces by doing the plumbing fixture and varying the moduli of this fixture. Okay, so let's actually do some plumbing first. So, let me give you the question. We'll do the counting as we go along the proof. So the question that you might ask is: Can you try to build up in a systematic way the whole moduli space of some genus G Riemann surface, by starting with, some given fixed sphere with 3 coordinate patches removed, and by doing the plumping fixture, varying the modulus of this fixture in all possible ways. Okay? This is a natural question to ask, and the answer to this question turns out to be not quite, but good, yes, to enough, but not quite in a particular way, and the positivity of this answer is enough to do what we want. So now let me tell you the answer to this question, the technical answer to this question. In what I'm going to say now, I'm giving you no proof. I'm just going to cite results from mathematics. Okay, so let's make the following statements. Okay, see, claim number 1: given any Riemann surface, okay, and given a non-contractible cycle, okay, given any Riemann surface, it is always possible to find a minimal area metric on that Riemann surface. Okay? By minimal area metric, I mean the following. I mean a metric such that the length of every non-contractible cycle, the length of every non-contractible cycle in that metric is greater than or equal to 2 pi. Okay? But subject to this restriction is otherwise minimal area. You see, talking about a minimal area surface for a Riemann surface without putting some other instruction, the other restriction is meaningless. Because, for instance, for a torus, just shrink it to 0. For any of these things, you just shrink it to 0, right? Since the Riemann surface is defined only up to a wild factor, you can always choose a wild factor such that the area of the metric is 0.
Non-contractible cycles.
Yeah. So, for instance, for the torus, the non-contractible cycle.
But there won't be any on the sphere.
There won't be any on the sphere. Yeah. So, So this would be a little degenerate from the sphere. So the statement will apply to every genus 1 or higher. Okay? Every genus 1 or higher surface. Okay? On the torus, what is this minimal area metric? That's totally clear. It's just a flat metric where each side is length 2 pi. That way, no non-contractible cycle has length more than 2 pi. Yes. But you saturate that, so you get a surface whose area is 2 pi, the whole thing squared. It's clearly impossible to have a smaller metric than that, a smaller area than that, because otherwise it would require one of the two sides to become smaller than 2 pi. Yeah. Okay. So on the torus, the statement is totally obvious. The claim is that on any genus G Riemann surface, G greater than 1, greater than or equal to 1, there exists such a metric. First claim. Okay. Now, second claim is a slight generalization of the first claim, and that's the following. Consider a Riemann surface with some marked points. Okay? Now, if we demand that a cycle that's a cycle that goes around one of these marked points is also considered non-contractible. Okay? Then the claim continues to hold true. It is always possible to find a metric on any Riemann surface with marked points, okay, of minimal area, subject to the constraint that no cycle around any of the non-contractible, no curve around any of the non-contractible cycles, including the cycles that circle marked points, has a length smaller than 2 pi. Now you might think of this last thing was really weird, because we've got, let's say, a torus, we've got a mark point, and you might think, well, I mean, I can go as near the point as I want. How can I prevent myself from having length smaller than 2 pi? But of course you can, depending on what the metric is. So the metric here, suppose this was at z equals 0 as our local point. Suppose the metric was dz by z over dz bar by z bar. Then the length around any cycle of this would be fixed. In fact, I may have to put some 2 pi's. It would be fixed and would give me, 2 pi. Okay? So basically, with this condition, you should think of working in a coordinate patch in which instead of having a mark point, you have this tube that goes up to infinity. Any disk can always be conformally mapped to a tube that goes up to infinity. And so you're looking at, you should work in those coordinates. And you're looking at a metric on a surface with tubes that go up to infinity such that the cycles of these tubes are also considered non-contractible, and they cannot have length smaller than 2 pi. Subject to that, you want to build their areas. Metric, some such thing always exists. Okay. So I'm going to give you many such claims and then we'll make a point. I'm sorry about this, but okay, it just wouldn't be worth it to go into some long diversion about how these things are proved. Okay, as long as the statements are clear, that will be sufficient. Okay. The third claim about this would be is the following. Let us define the band. Okay, any two minimal length geodesics that go around some non-contractible cycle, okay, that are homotopy to each other, that can be continuously moved to each other, are said to lie on the same band. Right? So on the minimal area torus, for instance, this guy and this guy lie on the same band. Can be moved from one to the other. Okay? Or on one of these things with a mark point, you've got this cylinder going up to infinity, and the whole cylinder lies on the same band. Okay? Now, the height of a band is defined as the minimum distance between bounding geodesics on the band. Okay, so suppose you've got a band and you can't go further on one side. Okay, so that's the end of one band, or that's one end of a band, and you've got a second end of a band. Now look at the minimum distance between points anywhere on this geodesic and anywhere in that geodesic. Okay, that is defined as the height of a band. Okay, finally, the perhaps a little most surprising claim of the lot is that every point on this minimal area Riemann surface lies in some band or the other, and bands might overlap. That is, given any point on the Riemann surface, it's always possible to find a minimal length geodesic that goes through this point. So obvious of the torus, of course. Okay, and it may be possible to find it in many different ways. Okay, so now we've got this good picture of this arbitrary height of this Riemann surface. Okay, we've equipped it with a metric. We've equipped it with a metric, which is this minimal area metric. That is minimal area subject to these constraints. In general, the data of string theory is just conformal classes, complex structures. But as an intermediate technical device, we've equipped the Riemann surface with an actual metric. Okay. Now I want to make the claim. The claim is the following. Suppose we look at all Riemann surfaces with arbitrary number of marked points such that the height of every band, every internal band on the Riemann surface is less than equal to 2 pi. Okay? And the height of every external band, one of these bands that are, these long tubes that are going up to infinity, is less than equal to pi. Pi. Less than equal to pi. Okay? Let's call the set of all such Riemann surfaces. The set of all such Riemann surfaces. Let's call that Vng. This is number of marked points. This is genus of the surface. Okay? So this is the set of all Riemann surfaces of genus G with n marked points equal to the minimal area metric such that the height of every internal band is smaller than equal to 2 pi and the height of every external band is smaller than equal to pi. Okay? Now we have to find the claim, and the claim is this: that associate every such Riemann surface with a vertex and endpoint vertex in a Feynman diagram. Okay? So suppose you want to build up the full moduli space. Suppose you want to build up the full moduli space at genus G, okay, with M insertions. The way you're supposed to do it is to make all Feynman diagrams that you can. Okay, using these guys as vertices. Using these guys as vertices, okay, which you put together with propagators, and the propagators represent the plumbing fixture instruction. Okay, so let me try to say this. Let's try to look at this let's try to look at this in an example. Okay. See, suppose you wanted to look at the sphere. Suppose you wanted to look at the sphere, okay, with 4 marked points. Okay, and by the way, the thing that you're supposed to start with in the sphere, you're supposed to start with V3G and anything that you can build up. Okay, so suppose you V30 and anything you see. Okay, so suppose you want to build a sphere with 4 marked points. Okay, then the basic Feynman graphs in your theory are associated, the basic Feynman vertices in your theory are associated with these spheres with 3 marked points. Now it's easy to build a sphere with 4 marked points. You can do this. Okay? However, in addition to this, there is also a basic vertex associated with the sphere with 4 marked points. Okay? And the basic vertex is, you look at the minimal area metric on the sphere with marked points, with 4 marked points, such that each of these stubs, these external stubs has bands, has length smaller than equal to pi. Okay? So the claim is that while you can explicitly cover a large portion of the moduli space of a sphere with 4 marked points by sewing together these 3 marked things, okay, you don't cover all of it. The part that you don't cover is precisely that part that gives you these minimal area scale, that is covered by minimal area metrics, such that the length of each stub, the height of each band, is less than equal to pi. Okay? And these basic guys, of course, these basic guys satisfy the requirement that their heights are also less than. So every vertex in your theory satisfies this basic requirement. Okay? And then the claim is that you put together the whole modularized space of the Riemann surface by making this final diagram joining of these basic Riemann surfaces plus all the new vertices at every n and every g. Okay. Now, I said this confusingly, and I've said I'm not trying to explain why this is true. Okay?
With the first diagram, for example, there are 4 of them which are less than pi, and 1 of them less than 2 pi.
Yes, though this is not a non-contractible cycle. You see, what have we eventually got? We eventually got a sphere with 4 mark points. And on the sphere with 4 mark points, in the end, there's only these 4 mark points.
There is no other.
Okay? Your question is very relevant though when you use this to make a surface with a non-contractible cycle. Okay? So suppose you use the plumbing fixture to take a sphere with 3 mark points and connect it to that. Like this to make a torus. You say that this plumbing fixture will give you only those toroids in which one of the cycles has length greater than equal to 2 pi. Because you join together 2 stars, each of which have length greater than each of which no. Yes. Okay. Wait. Sorry. No, if you say this, I'm sorry. When you do the joining together, you're supposed to do the joining together with stubs of length pi, but then with an arbitrary q parameter in this plumbing fixture. That will automatically make the effective length of this larger than 2 pi. You see, and we're only supposed to, I'm sorry, I should have said this wrong. Okay, we're only supposed to do it from q less than 1. Okay. Now you can set this very clear. Let me just think this through, make sure I'm saying this correct. How it does it external closure. You see. So I said something inaccurately. Let me say it correctly. Okay, this PNG represents all Riemann surfaces in which the internal guys, in which the heights of the internal bands is less than equal to 2 pi, but the heights of the external bands, the stubs that you leave, is exactly equal to pi. Okay, so you're supposed to take this thing, which has this semi-infinite guy going off here, and then cut it such that you've got a stub of length pi. Okay, now what I want to say becomes clear. You see, suppose you join together two stubs of length pi, you would get an internal band of length 2 pi. Now, when you want to do the integral over the whole moduli space of the torus, you should let the relative lengths of the two bands, which is the modulus of the torus, vary over everything. Okay? But you see, it's the plumbing fixture with Q less than 1. And so the claim is that you can do all this with the plumbing fixture always with mod Q less than 1. Okay? So the plumbing fixture with this mod Q parameter in every plumbing integrated from 0 to 1. Okay, that gives you the whole cover of the moduli space of Riemann surfaces. Okay, now what's the point? You see, suppose you had done this plumbing fixture with Q equals 1. I'm claiming the following. You take two of these stubs and you join them together. What you get is an internal band of length 2 pi. However, if you do it with a smaller Q, you get an internal band of longer length. Okay? Yeah. You see, why is that? What's basically going on is the following. Suppose you've got some patch here and patch here, and you make Q very small. Then you're taking a little bit of this patch and a little bit of this patch and joining them here. And joining them here. Okay? But if you did it with this metric, okay, so let's draw it. Suppose you've got some funny Riemann surface, but it's got some patch here. You take a little bit of this and plumbing fixture with a little bit of this, a small Q. Okay? And you smoothly interpolate between the metric that's here and here, you get something like this. But in this metric, it doesn't obey the conditions of our minimal area metric. Because this little tube here, its Q is so small, has geodesics that go down this cycle. It's going from here. Yeah. And geodesics that go down this cycle, which have length smaller than 2 pi. So you have to change the Y factor on this Riemann surface in order to make it our minimal area metric. Okay? And when you do that, since the Y factor adds isotropically, you draw this up to length 2 pi, you also draw this side up. Okay? So suppose there was something here that this was really, something internal. And this band would get blown up. Okay? So if you take something like Q, if you take the plumbing fixture with parameter Q, okay, if Q was 1, you would just add the lengths of these two stubs. But if Q was smaller than 1, what you would be doing is joining this at smaller size, and you'd have to blow this up in order to meet your conditions of your minimal area metric, and therefore be integrating over internal cycles of all lengths. Okay? So that's essentially the point. The point is that this construction in its vertices includes integrals over Riemann surfaces whose band heights are smaller than 2 pi. But all integrals over band heights larger than equal to 2 pi comes in the integral over the moduli space of the plumbing fixture construction. Is this clear? Shall we say it more? Shall I try to say it better?
Yeah, I'm not doing it.
Okay, let's. Can you try to isolate what you don't? Or is it so unclear?
For example, like you're trying to say that for q equal to 1, it would have been just pi and pi.
Yes.
And you're saying that for q less than 1, like no.
How does that go? Let's do it in one day. So what do we have? We've got these disks here and these disks, this disk here. Okay? And according to plumbing fixture construction, okay, suppose I take some very small cube. Okay? So I take a little region of this thing. Okay? And a little region of this thing, and I join them together by plumbing fixture. Okay? Suppose, this is a non-contractible cycle. There's some other tube here. So that we're talking about the length of a non-contractible cycle. If we want, there's no issue. Okay? But suppose we don't. Okay? So, what would I get? Okay. So what would I get? I would get okay, first let me say the pictures, and then if you want we can try to do it in formulas. Okay. What would I get when I join these two things here? I would have this little tube joined to this little tube. This little thing joined to this little thing. Okay? Suppose I use some arbitrary metric. Suppose I use some arbitrary metric to describe this structure. But arbitrary metric, I mean arbitrary Y factor. Okay? Always say the formula class. Okay? Something that smoothly interpolates between the metric of this surface and the metric of this surface. Okay? Then both of these remain very small. So what I get is a surface that looks like this. Is this clear? Now this surface does not obey the conditions of our minimal area metric. Okay? Because there is a non-contractible cycle, like this one, where there is a geodesic, there's some cycle going around it, whose length is smaller than 2 pi, because it makes q very small. Is this clear? Yeah. So I have to change the Y factor in order to put it into this minimal area. Okay? But the Y factor acts homogeneously. If you blow up one length, it blows up all lengths. Okay. So, you see, this construction in this metric makes this of length 2 pi. But now we have to move to the Y factor such that this length was at most 2 pi. In this construction, it will be, I can't remember what, but it will be like something like 2 pi times q, or maybe q times q bar or something like that. Okay? So it's very small. So we have to blow it up. So in doing that blow up, what we will get is that this length can be made 2 pi, but then this length will become 2 pi divided by q. Or maybe q times q bar, we have to do this more carefully. You see what I'm saying? Yeah. Okay? So therefore, if you just integrate over all q less than or equal to 1, okay, you will automatically generate those parts of the Riemann surfaces where band heights are greater than 2 pi. You won't generate band heights less than 2 pi. That's why those guys are integrated over in your definition of the Feynman vertices. That's roughly what's going on. Okay, good. So now, this is something I nowhere near proved the statement. I'm just telling you about a result that is claimed that mathematicians know the answers to. Okay, I've never seen the proof myself, and I hope I never have to. Okay, okay, yes. Okay, so okay, but the statement is clear. Now, why is this important? Okay, this is important for the following reason. You see, it's important for the following reason. See, where are the points in moduli space? Where are the points in moduli space? Okay, where are the points in moduli space where you expect divergences from? Okay, the key point is that you expect divergences from extreme corners of moduli space. Why is that? For instance, suppose we look at the Feynman diagram. You have a Feynman diagram interpretation of what's going on. diagrams blow up. Feynman diagrams blow up at very high momenta around loops, or from a position space point of view, where the insertions of the operators come very near to each other. Okay? Or, yeah. So, basically, if you go to very, very short, if something's propagating over very, very short distances, okay? Now, very, very short distances compared to the size of the string. So, it's an extreme corner in moduli space. You see, the length of the propagator is going to 0 compared to the height. Or 2 points are coming very close to each other. That's another extreme corner in moduli space, because the moduli include the positions of the operators, and the operators merging with each other is some extreme corner in moduli space. Okay? So this is the final diagrammatic interpretation, final diagrammatic way of saying it. And if you think just more structurally in terms of Riemann surfaces, basically interior points in moduli space, there's no scope for any divergence. Everything is nice and smooth and regular. Okay? The only place where you could get a divergence from is where something funny is happening, something is going to infinity. Okay? And that happens at extreme corners in moduli space. We've seen this in the torus, for instance. Right? We saw this in the torus when we were integrating over this region in moduli space. The only place where divergence could have happened was this thing going off to infinity. Or from here, of course, this guy. Sorry. It's at this extreme corner. So apparently UV divergence. It's the same kind of phenomenon that you expect always. Now, because of that, this VNG, the vertices that you've added to your graphs, and because they're integrated, that includes some integration in moduli space. But that integration is over some very internal region of moduli space. We're ensuring that by demanding that no cycle get too small. Do you see? We're ensuring that no band, which is the size of any cycle, get too small. No cycles get too small. So we're not allowing, say, one cycle of the torus to shrink to 0 compared to the other one remaining finite, which would be an extreme corner of moduli space. Okay? So these vertices that we're adding are safe. All of the divergences, the potential divergences in the theory, are going to appear from the integral over the moduli of the plumbing fixture. Okay? So divergences and imaginary parts, things that have to do with unitarity, we can isolate by understanding this plumbing fixture construction level for conformity theory. That's the key idea. Okay. So now, there's just one more thing. I'm sorry, this is going to be a very formal lecture. This will be the last very formal lecture. Then we get on. Okay. We get on calculations next. Okay. So, so far this lecture has been about geometry. But now let's turn to conformity. Okay. So suppose you've got a Riemann surface with some marked points. Okay? And you want to do the path integral over the Riemann surface that you form from the plumbing fixture construction. You want to do the path integral of the conformity theory with these vertex operators. Okay? Then you form from the plumbing fixture construction. Of these two different Riemann surfaces. Now, you see what's going on. What the plumbing fixture construction essentially is cutting the Riemann surface on a circle, cutting the other Riemann surface on a circle, and joining these two. But the path integral of this conformal field theory with this circle cut is some state. Right? You know, what you would have here, is that the path integral of the formal field theory with this disk removed is some state on the CFT in ordinary radial quantization. Similarly, the path integral of this thing here is some state of the CFT in ordinary radial quantization. Okay? And what you want to do is to join these things up. You want to join these things up with the insertion of the identity operator. But just as we did for the analysis of these 4-point functions, okay, we can resolve this identity operator into a sum over internals, a complete sum of states. So instead of looking at the now this complete set of states, you see how you make this complete set of states. You make the complete set of states by putting in a complete set of operators into this disk. Okay? So it's statement. Let's first do it for q equals 1 and then we take the rest of it. Suppose you have a Riemann surface that is constructed by the plumbing fixture construction of two different Riemann surfaces. The path integral of the conformal field theory on this bigger plumbing fixture sort of Riemann surface is equal to the path integral on each of the constituent guys with every operator in the theory with operators inserted at the centers of the disks that you've removed, okay, and then the factor of GMN, the inverse of the homological metric, put in and summed over this thing being AM, this thing being AN, summed over all of it. You see, once again, what's the logic? You've got this tube here, you insert identity. Identity is the sum of all states. But each state is filling up this thing with a disk with an operator. Okay? So let's say again, we've got this tube here. To cut it. On this cut, you insert identity. But identity is equal to sum over Mn with GMN. Okay, we should really say this thing. Mn with GMN. Okay? So it's the same thing as this conformal field theory with state M inserted. Yeah? And this conformal field theory with state M inserted. But what is the state M? The state M is filling up the thing with a disk with operator M inserted. So it's undoing the plumbing fixture construction so that you decompose it into its constituent pieces. You're undoing the plumbing fixture construction so that you decompose it into the constituent pieces, but add an operator M where the construction is undone, and an operator N where the construction is undone, and put this factor of GMN. And put this factor of GMN and put the factor of GMN and sum over all operators. Okay, now this was true when Q is equal to 1. This was true when Q is equal to 1 because in our conventions, a state is created by inserting an operator of length 1, an operator at the origin of a disk of size 1. That gives us the state operator map. Okay? Suppose we were working with Q less than 1. Then what we're getting is not quite the same state. Right? Because then inserting the operator at the center of the disk produces not quite the same state, but there's an easy way of fixing this up. You see, just work with a new coordinate. So instead of using the coordinates Z1 and Z2, work with the coordinates Z1 divided by square root 2. So let's say Z1 prime, and Z2 divided by square root 2, Z2 prime. In those coordinates, these disks are each of length 1. Okay? So in these coordinates, inserting identity is precisely inserting GMN AA. Okay? But the insertion of A operator in these coordinates is related to the insertion of the A operator in the other coordinates by a factor of dz1 prime by dz z1 to the power h, and z1 prime tilde by z1 tilde to the power h. So when we work that through, when we do the clumping fixture construction with parameter q, what you get is a factor of q to the power h, q bar to the power h, gmn times the constituent surface with an, the constituent surface with an, and then all the other surfaces, all the other insertions. Okay, so let's understand the claim. The claim is that if you take the Riemann surface that is constructed out of two other Riemann surfaces with a plumbing fixture with parameter q, okay, then the path integral with some number of insertions on this Riemann surface is the same as the path integral on the constituent Riemann surface, the guy that you used to make the plumbing fixture, okay, with all possible operators inserted at the origins, summed with gmn, summed over all n and all n, but with the factor of q to the power h and q bar to the power h added. Remember that the integral over all Riemann surfaces, okay, includes an integral over all q. Okay, extreme limits of Riemann surfaces are obtained when some plumbing fixture q goes to 0. That makes these lengths very, very long. Okay, we're working in a metric in which no length is allowed to become very short because it's minimal, right? So the only way to get an extreme limit is for something that becomes very, very long. Okay, great. Now the last, basically, at the end of this lecture, if we have time, but the last statement I'm going to make without trying to justify it in detail, again, appealing to our discussion of the torus, where we did the same thing very carefully and found the same answer. In string theory, in addition to all this business, we have to put in a B insertion for every modulus. So the integral over Q is accompanied by a B0 bar insertion. So we get GMN along with the B0 bar, which gives us the same nice property that we discussed for 4-point functions, that it links only states that are annihilated by B0 with that states annihilated by B0. And in addition, we also get a factor of QQ from the insertion of from the insertion, from the form of the B insertion in the scattering matrix. This form that was. We found the same factor of 1 over m tau square in the discussion of the torus. It's the same kind of discussion. I'm not going to try to derive it. Okay, fine. Now, with all this accepted, now we can see the point. Why did I go through all of this? You see, the dangerous part of Feynman diagrams, as we've seen, is associated with some q going to 0. Okay? So let's understand what we get from the limit of some q going to 0 of this plumbing fixture construction. Okay? So what we have here is some amplitude times some other amplitude, and now we've completely isolated the q dependence, just like we did in the discussion of 4-point functions, using this insertion of complete set of states. Okay? And just as in that case, what we get is q to the power L0 minus 1, q bar to the power L0 minus 1. Okay? Then we got this q to the power L0 minus 1, q bar to the power L0 minus 1. Just exactly the same way as in our discussion of 4-point functions. We have to do this integral over d to q. But now this is the same integral we had in this discussion of 4-point functions. And for exactly the same reasons, brightness and radial coordinates, you get rid of 1 dr. d to q has an explicit factor of quad q, and then there's an integral which removes another mod q. So what you get here is 1 over m squared plus k squared plus minus I epsilon up to subfactor of 4 alpha prime. And then there's some 2 pi's and so on that we're not keeping track of. Is this clear? This is now exactly parallel to the discussion that we had for the 4-point functions. Is this clear? It's rewriting L0 and L0 bar in terms of the mass square and momentum square of the vertex operator. And just go through the same discussion we had last lecture, and you get this. Okay, good. So this gives you the integral over q from 0 to 1. The key point is this, that we have completely isolated the dependencies, the behavior of all these diagrams in the region of moduli space where they're dangerous. Namely, where some q is very zero. Okay? And what we find is that this behavior is precisely given by Feynman diagrams, by the behavior of Feynman diagrams, and in particular all possible divergences. So now there are 2 things. Firstly, the imaginary parts of these amplitudes. The imaginary parts of these amplitudes are in one-to-one correspondence with the imaginary parts of a Feynman diagram expansion, with internal particles propagating in internal channels. Okay? And so if you think this through, and we've not done it as carefully as you need to, but so because of this point, if you think this through, the usual arguments of Feynman diagrams giving you unitarity in field theory just go over in a straightforward fashion to imply unitarity for string theory amplitudes. Okay? The imaginary parts are the imaginary parts of Feynman diagrams of propagators associated with each propagating particle. Okay, and that essentially results in the unitarity of the string limit. Okay, the second point I want to make is that you see the dangerous regions in moduli space. The dangerous regions in moduli space, which have to do with propagation over very large distances, which have to do with the skew goes to 0 limit, have all been identified with propagations of particles in space-time over very long distances. Okay, so while string theory can have divergences, for instance, the bosonic string theory does have divergences, these divergences can always be interpreted as long-distance effects. You see, every dangerous region in moduli space has just been associated with poles of particles propagating over long distances. Okay? So while string theory can have divergences, these divergences are always interpretable as IR divergences associated with long distances. Now, why is that an improvement? You see, this is an improvement because an IR divergence is a physical thing. An IR divergence tells you that you're working with, say, the wrong background, or you're expanding your theory with the wrong masses in your propagators or something like that. Okay? It may represent an instability in the theory, in which case you're working with an unstable theory. Okay. But if your theory has no physical instabilities, see, IR divergence is always associated with either asking the wrong question, like trying to calculate some scattering amplitudes for gluons in QCD, or with doing an expansion around the wrong background. You know, if you do an expansion around a maximum rather than minimum in a quantum field theory, your expansion will be full of IR divergences. Okay? So, all the divergences that can occur in string theory are associated with physical effects. Now, it could be that you're looking at a string theory in which you've not got the right background, or your background has a maximum rather than minimum, you will get ion divergences, and you should. Because if you weren't doing expansion under stable minimum. However, if you cure all ion problems in the theory, if you work around a good background, like the background for superstring theory in superstring states, so that your theory has no ion divergences, then your whole string amplitude will be finite. Okay, so that is the second main point I want to make in this lecture. Okay, now let's see. Yeah, so this has been a strange lecture because it had very few equations. I don't really know what to do about that. To add more equations, we have to do much more work. Okay, perhaps we should just leave it at this. So is there anything else I wanted to say? Anything else I wanted to say? Yeah. Okay. There's some very general discussion that I recommend you read in section 9.5 in Bulchinski, in which he talks about what's called the Fischler-Susskind mechanism. Okay, in which he talks about how in which he addresses the following question. You see. In which he addresses the question about the following question. You see, the equations of conformal invariance. Okay, maybe we should let me just say the equations of conformal invariance, as we will see when we come back, when we reconvene to discuss our class again. The equations of conformal invariance on the sphere give us the tree-level space-time equations of motion of string theory. But now there seems like a puzzle because these equations of motion get corrected at loop order. But how can equations for consistency of string theory get corrected at loop order? You know, the equations are just some local property of conformal field theories. Okay, conformal invariance is not some global statement. You know, beta function matches the local statement. How can that get corrected depending on what manifold we're working with? And the answer is that the integral over moduli space has to be regulated, and that integral over moduli space has its own that regulation has the wild factor slips in that regulation, more or less in the way that the wild factor slipped in the regulation of OPs when we try to define e to the pi kx, for instance, the derivation of pi kx. Okay, this discussion will make more sense once we have gone through the discussion of the beta function just on tree level. Okay, so I'm not planning to go through to discuss it now, but I suggest you. I mean, it would be a good thing for you to do. Okay, so I think that we probably want to just stop this lecture here, apart from questions and comments. I'm sorry, I know that this would feel like a very unsatisfactory lecture. What I hope I've conveyed in this lecture is a general sense of the issues of unitarity and finiteness of loop amplitudes in string theory, though in this very fuzzy way. Let me just try to summarize this general sense. And then let's take questions. The key point is the following. You see, in doing the integral over the moduli space of string theory, you have extreme corners in moduli space. Okay, let's first see it with the torus. Suppose you do the integral over the moduli space of the torus. You have this region where one of the cycles of the torus becomes very small and the other one becomes very large. Okay? Now, suppose you think of the one, it's only the ratio that matters, so it's one of the cycles becoming much smaller than the other. Now, suppose you think of the cycle that's becoming very small as the time direction. Okay? Whereas the cycle that is remaining large as the space direction. From a quantum field theory point of view, how would you interpret this? You would interpret it as each of the particles of string theory going over a very small loop in space. Going over a very small region of Schwinger parameter space. This is the region that would give you divergences in quantum field theory. Is this clear? Is this statement clear? You remember how in our discussion of torus amplitudes, we looked at the close relationship between Schwinger parameters of field theory and the moduli space of string theory? You remember how we reconstructed the torus amplitude by summing over the Schwinger parameter representation of the one loop path integral for each particle. And in that reconstruction, the Schwinger parameter was simply just part of the moduli space of the torus. You remember that, right? So one side is the length of the string, the other side is how much time it runs on, how long it goes in Schwinger parameter space. Okay? So the region in which you go a very small circle in Schwinger parameter space is associated with UV divergences of field. Okay? So this is the dangerous region that we should be studying. However, we can take another point of view. We can regard that cycle as space and the other one as time, as Schwinger parameter. Then perform a Weyl transformation, so that guy stays with length 2 pi. But on doing this Weyl transformation, what happens to the other guy? It becomes very long. Okay? So the region of potential damage in field theory space, the region over which you go over a very small circle in Schwinger parameter space, cannot be problematic unless there is also a problem in some other region. Namely, where the Schwinger parameter length becomes very large. The Schwinger parameter length becoming very large is associated with propagation over very long distances. Okay? Remember what a Schwinger parameter is. It's e to the power minus tau times k squared plus m squared. So if tau becomes very long or very large, you're getting contributions to small k. It's got an inverse relationship with k. Okay? And therefore long distances. Tau is like length squared. Okay? So on the torus we've already seen this, but I want to emphasize it because today's lecture is how it's homogeneous. Is about how it's homogeneous. The point is the following: that it's impossible. First point about UV parameters. It's impossible in string theory to have a problem in the UV unless you also have a problem with the IR. More precisely, there's always a way of looking at looking at the moduli space of Riemann surface in the string theory, such that all extreme limits are always interpreted as IR extreme limits. Okay? Then if your theory is IR finite,